Peace, Amy.
Okay. Thank you so much for the invitation to present here today. It's especially nice because as a grad student, I spent some time actually at Ghent University, and more recently, I got to visit both KTH and also Delft this past summer. But today I'm going to talk about science-based advanced manufacturing of metals and alloys, and I want to acknowledge the large number of people that have contributed to this work I'm going to show today, especially students and postdocs and different colleagues. Shown here in bold are actually some of my current and former students and postdocs, and in italic are some of the students and postdocs of some of my colleagues involved in the work I'm going to talk about today. Um, Okay, so this is sort of the concept of, I think, where our work started, and I think this still holds true today. And really, the aim of our work has been multi-scale prediction and control of metallic alloy solidification dynamics. And really, what we start with is typically in situ characterization and visualization of the way that microstructures develop. So we normally start with some metallic sample, and this can be anywhere from 100 nanometers up to millimeters in thickness. We use different tools and probes to watch metals while we process them, in this case during solidification. And this could be X-rays or protons or electrons, just as different examples. And then we make movies of solidification dynamics. And because we have the opportunity to see the way that the microscopic structures actually develop during solidification, we can couple this sometimes with controlled processing as well, where we can directly affect the way that those microstructures develop in real time. And then we like to couple that with model predictions that are multi-scale. So up in the upper corner here is an example of a dendritic array in aluminum copper from one of our synchrotron X-ray imaging experiments. And then just below that is a complementary dendritic needle network simulation done by my former postdoc, Damien Touré. And then on the opposite side, at a larger length scale, is an example of an 800 MeV proton radiography or PRAD casting filling, a mold filling, and then above that is a continuum scale computational fluid dynamics simulation. So length scale is important in our work, but also time scale as well, and that becomes important obviously when we talk about things, especially like rapid solidification. And really, the aim has always been to kind of integrate the experiments and the models together. So, I'm going to start with an example of the type of information we can get from some of these real-time imaging during processing experiments. So, I'm going to show a movie of synchrotron X-ray imaging of a near eutectic aluminum copper alloy. And here we're doing controlled directional solidification and melting. So just for context, this is a 200 micron thick film, which is on the order of about the diameter of a human hair. So this is a very thin film sample. Here we've actually stopped a planar solid liquid interface in the field of view for the imaging. And in the lower half, you actually see the solidified two-phase eutectic microstructure that appears lamellar in nature. So the bright regions are the aluminum-rich phase, and the dark regions correspond more toward the Al2Cu phase. And then above, we have the alloy melt. So I'm going to show you a top-down directional melt, and you'll get to see some interesting dynamics that happen. So on the melt, you actually see the breakup of the eutectic structure. You see the aluminum rich phase kind of float off into these matchstick kinds of fragments. And you certainly see things like convection happening in the melt. So taking that a step further, again, being able to have the benefit of seeing microstructures while we process them, this is an example of what we call sort of an artificially process-derived composite in an aluminum eutectic composition for aluminum copper. And what you're seeing here is now a solid liquid interface that we've stopped in the field of view. And we're going to do a series of melt back and solidification steps. So up on top here is our solidified eutectic, and then you're going to see a melt back of the interface. And this is again on the order of about 200 microns or so. So here we're melting back the interface. And here in the previous example, you kind of saw the eutectic break up into those matchstick bright aluminum rich fragments. Here you actually see those aluminum rich fragments are sort of spheroidized and coarsening. And the aluminum rich phase is lower density. It's buoyant, so it actually floats at the solid liquid interface. And then as we move forward, we trap in that layer and then sort of wash, rinse, repeat. We create another layer and create this artificial composite kind of microstructure. So it's pretty amazing the type of control that we can have on microstructure development during these in situ kinds of experiments. And we can see the way things develop and start manipulating microstructures. So lots of our early work really focused on, I'd say, more conventional solidification processes. So things like directional solidification, metal casting. And if you open a solidification textbook like Kurtz and Fisher, you see a nice diagram like this that provides thermal gradient G and solid liquid interface velocity V. And those different combinations of G and V impact the interface stability and determines the patterns that we develop during solidification. And so we can have a planar solid liquid interface, cells, or these hierarchical dendritic tree-like structures through different G and V combinations. And really, as I mentioned earlier, our early work focused on this diffusion controlled growth regime where things like solute and heat transport are very important. So one of the first sets of experiments we did, these are again examples from 200 micron thick foils of aluminum copper, a very dilute aluminum copper alloy, is we actually mapped out this processing space in real time, the G and V combinations that give us the different growth regimes and the growth regime transitions. So shown over here on the one side is an example of the different interfaces we can generate in the solidification patterns. So we can have a planar solid liquid interface, these cell-like structures or hierarchical type dendrite structures. And then on the other side is an example of GV mapping we kind of did in real time. And here, the majority of the experiments that we did were bottom-up directional solidification. And what's interesting is solidification theory, this black line here would predict the regime transition from planar to cellular over here, where in reality in experiments, we see it shifted to much higher velocities. So this was a question that we had about why are we seeing higher velocities than we might expect. And so we did a series of sort of very specific top-down directional solidification experiments. And it shows that the velocities we see the growth regime transitions at even shift to higher velocities. And so the thing we kept coming back to was convection in the melt. And I'm going to show you an example that I hope kind of convinces you of this. So the work I was showing you was on a very dilute aluminum copper alloy, which doesn't have great contrast in the synchrotron X-ray imaging. But I'm going to show you an example for tin bismuth, which shows it a lot more clear just to illustrate the point. So this is actually going to be a false colored synchrotron X-ray movie with top-down directional solidification. So you're going to see tin-rich dendrites sweep into the field of view. And then you're going to see the bismuth solute, which is colored blue, I believe, kind of falling in plumes in the melt. And you'll see sort of the enhanced effect of gravity here. So here comes the array, which I think is colored red. And then you see the blue bismuth solute, again, falling in plumes. The bismuth solute is higher density, right? So we're kind of taking advantage of the enhanced effect of gravity here. And so an important point about this example is this is even a thinner sample. This is thinner than 200 microns. And we see, even in these thin constrained samples, we still see convection in the melt. So why is this important? If I took this to one of my colleagues, like Alain Karma at Northeastern University, and I asked him to do modeling of the microstructure, in the first pass, they likely wouldn't incorporate the convection in the melt. And that's sort of what you see here. So this is an example of our synchrotron X-ray imaging as compared to 3D phase field simulations that were done by a lens group. And if we look at characteristics of the microstructure, so for example, tip radius versus velocity, here are experiments that are all the open points compare well with simulation results. That said, when we go to primary dendrite spacing versus velocity, the open points are the experiments, and in red are the first simulations that were done that ignore the impact of convection in the melt, and we get the wrong trend that doesn't match the data. So if we think about solidification, we end up building up a solute boundary layer during directional solidification, and we know that we have convection in the melt that impacts that. And so what we did is we actually truncated the solute boundary layer. And when we do that down to about 100 microns or so, now we have good matching with the experiments. So I do like to show this example because it actually shows that these in situ experiments are actually telling us what physics is missing from the modeling such that we can be predictive about microstructure development. Sort of on the other end of things, metal casting. As I mentioned, we have done some of these kinds of experiments. This is an example I'm going to show of 800 MeV proton radiography or PRAD that was done at Los Alamos National Laboratory. And this has benefits such that we can look at a much, much larger field of view. We can also look at high density metals and alloys that would be more difficult with synchrotron X-rays. So in this example, I'm going to show you uh, an alloy melt, eutectic tin bismuth. That's halfway up the crucible, and then we're going to sort of be dropping in molten bismuth liquid. So you can see the actual the fluid flow patterns that develop in the melt. So it's pretty cool that we can see that, and seeing that type of flow behavior can be important for things like computational fluid dynamics and really understanding and doing casting design. And so that's some of the work that we've also done in the past. So this is a nice example of 800 MeV proton radiography. These are snapshots of metal casting, looking at the casting fill process. Down here is just a little schematic of the graphite mold assembly that we use. And then you can see we're sort of loaded up with thermocouples so we can measure the temperatures and really start doing some comparisons. So one of the things that's always of interest to us is, and when we're doing the modeling, are we getting that right? And so this is an example of work done by my student Nadira Shragani, where she's taken this PRAD movie and she's done some Flow 3D cast modeling using different assumptions about the metal mold heat transfer coefficients to match with the experiments. And in this case, actually, Model 2 ended up better matching the fluid flow we see in the experiments. And then, as I mentioned, we load this up with thermocouples. So this is an example over here of this sort of zoomed in region here of the thermocouple traces as directly compared to the modeling results for these different metal mold heat transfer coefficients. And what was kind of interesting about this is that Model 1 actually did a better job matching, but as I mentioned, Model 2 did a much better job with the fluid flow. So Nadira actually ended up going with Model 2 in this case. We also know from the microstructure, we can look at characteristics about the microstructure, things like primary or secondary dendrite arm spacing, and we can relate things like that to cooling rate. So this is just an example micrograph of the top of the casting, which is much, much coarser than the bottom of the casting, which has a much, much finer dendritic structure. And here she's just doing some comparisons in terms of secondary dendrite arm spacing. So again, this has a lot of potential impact to better understand metal casting and to better understand casting design. And we have done some PRAD experiments looking at microstructure development as well. So another area that's always been of interest for us is going beyond sort of now these conventional solidification processes to things like rapid solidification that you might encounter with, say, additive manufacturing as an example. So again, this is our GV map, and we really focused on this diffusion controlled growth regime in early work. And then the question is, what if we go to higher solidification velocities, and what types of experiments and modeling can we do to better understand that? And that sort of guided our sort of next follow-on work, which has been working with my colleagues at Lawrence Livermore National Laboratory for many years, doing dynamic transmission electron microscopy or DTEM. To look at rapid solidification. So this is a very specialized technique, and this is a microscope that they have at Livermore. And basically the way that it works is you sputter deposit 100 nanometer thick film on an amorphous silicon nitride substrate. You can then hit this with a laser and you can create a molten metal pool, and then you can watch solidification dynamics at very high spatial and temporal resolutions, much higher than you could do, for example, with synchrotron X-rays. And one of the neat things about this is that because you have a thin film kind of sample geometry, you mitigate things like convection in the melt. So this makes it really nice to compare with solidification theory. And so this is an example of one of these spot melts in a DTEM movie. And then importantly, we can pull out quantitative information. So this is solidification velocity versus time. And here you can see some different growth regimes. In this case, we have an incubation region, and then we sort of have a directional rapid solidification. And when we hit about 2 meters per second, so this is very high velocities for solidification. In this case, we actually end up having a banded growth morphology in the central region of the melt pool, where those highest velocities are experienced. And these types of morphologies have been predicted by solidification theory. So here in the central region is this banded growth, and this basically is associated with local acceleration and deceleration of the interface and the local solute conditions that drive this. And so that's been seen with DTEM, which is actually pretty neat. And so one of the things that's challenging, I think, from the modeling point of view, is doing this quantitative phase field modeling of microstructure evolution for rapid solidification conditions. So working with my colleague Alen Karma's group, at Northeastern University, they've really been pushing forward in this area to try to be able to do phase field for rapid solidification. So this is an example where they're taking into account the prediction of velocity dependent properties, things like partitioning coefficient, the liquidus slope, and then we're directly comparing that and validating that with our DTEM data. So this is an aluminum copper example, again, where we see banding in the central region of the melt pool. And here a 2D phase field simulation from this new implementation of their model. And we can actually see that they do indeed predict the banding. And one of the important things about this model is that it includes latent heat in this particular model. And these are some nice simulation results. Hopefully these movies play from my colleague Alen Karma's group. And this just shows two example simulations, one without latent heat and one with latent heat. And basically the impact of that is on the length scale of the bands that we develop. So without latent heat, we form a much coarser microstructure as compared to including it. So it highlights that that's important in terms of actually getting those quantitative predictions with our experimental data. So now that we have that newer model for rapid solidification that we validated with aluminum copper, we've been doing a lot more in this space more recently. So this is an example in aluminum silicon, extending some earlier work that we did on directional solidification, looking at grain competition, but now during rapid solidification. And so the nice thing about DTEM is that we know we get the interface position with time. So we have an idea of where the interface is during the growth. And then if we couple this with post-mortem characterization, so here we're doing crystallographic mapping in the TEM, we actually can get the texture evolution with time and again start looking at things like grain competition. So this is an example from some new work that just got accepted to Nature Communications and should be coming out here pretty soon. But basically we're looking at that grain competition and the texture evolution with time during rapid solidification. And one of the neat things about this is we came up with a statistical analysis approach, basically to look at the grain competition, and the results really suggest we have a transition to 011 type growth during late stage solidification. And this has links and is really tied to anisotropic effects, especially of the excess interface free energy that plays a dominant role. And so this is an area we're going down right now, again, looking at things like grain competition, looking at things like dendrite orientation, transitions, tied to the anisotropic effects, for example, and also even looking at pattern selection and concentrated alloys relative to absolute stability is another area we're working in. So I showed this schematic earlier of a Kurtz and Fisher kind of schematic, and you see that again in a solidification textbook. And if you open a welding textbook, often you'll find a sort of a riff on that diagram. So this is now temperature gradient versus growth rate, R. Usually growth rate and velocity you'll see kind of interchanged on these diagrams. And not only do we have sort of the planar cellular dendritic regimes sort of broken out, we also have a distinction between the columnar and the equiaxed. So this is called the columnar to equiaxed transition, or CET. So this is where we go from elongated columnar like grains that might have anisotropic properties to more equiaxed refined grains that you would expect to have more isotropic properties. So the CET is important in the context of additive manufacturing, especially. And then in addition, not only does G over R or G over V determine the morphology of the structure, which we've talked about, G times R determines the length scale of the microstructure. So fine or coarse, and that can impact things like fatigue performance of materials, just as an example. So, kind of with that in mind, this is some really nice work that came out of Ryan DeHoff and coworkers at Oak Ridge National Laboratory. And this is microstructure control in Inconel 718 by electron beam additive manufacturing. So here you're looking at gradient versus velocity and this columnar to equiax transition, or CET. And here you're looking at the GV conditions that are experienced relative to the CET, which has a very big impact on the microstructure development and allows you to basically have some control over microstructure development during processing. So this is an example where they basically crystallographically spelled out Department of Energy, or DOE, in the microstructure by turning on and off the columnar to equiax transition during processing, which is actually pretty cool. And a more recent update on this is this comes from Plakowski et al. Here they've actually made the Mona Lisa in the microstructure by turning on and off columnar to equiax transition, which is pretty neat. But it really illustrates your ability to, again, control microstructure development during processing by understanding the conditions being employed. And I do want to highlight that CET is important for additive manufacturing, but it's also important in conventional solidification processes as well. I had previously showed you this top-down directional solidification for tin bismuth. I'm going to now show you the bottom-up version. And what you'll see in this case is you'll see the dendrites bottom up, I think colored red, and then you see the blue bismuth solute kind of settling. Again, it's higher density. And then you can see sort of the fragmentation of these tin-rich dendrite arms off into the melt. Again, they're more buoyant, they want to float. And those kinds of events can actually trigger columnar to equiax transition, for example, within a casting. So it's also important to metal casting as well. So the extreme end of rapid solidification that we look at with DTEM, where we're really looking at velocities on the order of 1 to 2 meters per second. For additive manufacturing, we actually have to dial this back a bit. Usually we're looking at velocities of a meter per second or less, really sort of tenths of meter per second. And so this is some work that we've done trying to better understand additive manufacturing. And this is in collaboration with Teresa Pollock's group at UCSB. Teresa basically provided us some nickel moly aluminum single crystal samples, and these were given to us as pigtail single crystal castings. And the neat thing was then we could strategically cut out specific orientations to look at and do these really clean sort of studies. And now here we're doing synchrotron X-ray imaging of these single crystals with different power conditions doing simulated additive manufacturing. So the way that this works is you have an X-ray beam that comes in, you've got the location of your sample, which can be a thin film, it can be a film with powder on top or just a packed powder layer. The laser beam comes in, impinges on the sample, you can create a molten metal pool, a spot melt or a raster, and you can be optimized for imaging or diffraction. But this is a nice example of one of these spot melts of a single crystal, and you can see the sloshing kind of a liquid in the melt pool. And then we can also importantly now track the solid liquid interface, or the velocity. So looking at velocity versus position from edge of the melt pool for different power conditions. Some trends kind of fall out. So for higher power conditions in general, we tend to see lower velocities in general. Where we have lower power, we tend to see higher velocities. And we do tend to see higher velocities sort of towards the tops of the melt pool. We can then couple this with postmortem characterization. So this is an example of polishing into the midplane of these samples. And you can see for the high power conditions and doing crystallographic mapping, we're able to retain the substrate orientation, which is actually pretty neat if you're interested in things like repair scenarios of single crystals, as an example. And then for the lower power conditions, you see some new grain orientations at the tops of the melt pools where the higher velocities are experienced. And this kind of summarizes some of those results. So a couple different compositions, a bunch of different orientations, different power conditions. And I've already sort of talked about velocity versus power. But again, we can look at characteristics of the microstructure. So this is now um, primary dendrite arm spacing versus power. And one thing that falls out of this that is really illustrated nicely for this higher moly alloy is we can see at the bottoms of the melt pools, we tend to see much more refined microstructures as compared to the tops of the melt pool, which is sort of interesting. And so why is this? When we go to higher powers, we tend to have more chaotic melt pools and often have keyholing and keyhole collapse that happens. So this is an example of a high power condition where we have a keyhole collapse, where we have a spike in velocity, and then it's sort of business as usual for the rest of the melt pool solidification. And if we go in and we look locally at that keyhole collapse region, we actually see some new grain orientations. So we have a velocity that's high enough to trigger columnar to equiax transition and sort of those much finer kinds of microstructures as well. And we tend to see that at higher power conditions, which does make sense. So the GV construct allows us to understand microstructure, but also the formation of defects as well. So moving forward to model some of this kind of data, we felt like we really needed a handle on not only the solidification velocities, but also the thermal conditions that are experienced in the melt pool. So to do that, we started doing Flow 3D AM simulations. And so here we're actually doing a set of simulations for one of these spot melts and comparing head to head the velocity versus time of the Flow 3D CFD simulations to our radiography, which match well. And then we did some nice destructive characterization where we compared Flow 3D radiography, destructive scanning electron microscopy, and also 3D tri-beam, which is a novel technique developed at UCSB that allows us to do 3D characterization of the melt pool. So an example data set is shown here for one of our spot melt conditions. And so now that we have the sense that we have fairly good matching across these techniques, we have the velocities sort of bound, we believe them. Now we feel better about the thermal conditions, so we can start moving forward to model microstructure development. And some of the early work that we did, this is an example of those spot melts, two different orientations for a given power condition. And if we look post-mortem, we see from sort of some of our earlier on assessments that we actually see dendritic microstructures, even though solidification theory would predict that we were beyond absolute stability. And so we know there's some effects that we need to deal with here in terms of the modeling. And so now that we have a lens new phase field model, that's a direction we're going in is better modeling of these nickel moly aluminum ternary samples, including perhaps in 3D. And I want to mention this is a simulation done with exascale computing by one of my colleagues at Los Alamos National Laboratory of an approximation of this alloy of a nickel aluminum binary composition. So a full 3D melt pool simulation with phase field. So again, better trying to predict for multi-component alloys and also sort of in 3D as well. And then above is just a nice example from Peter Voorhees' group at Northwestern, where they were doing some of this columnar to equiax transition modeling for us for multi-component alloys and making comparisons with our data. So moving forward now, we hope to start doing some meaningful modeling of these data sets that we have for microstructure prediction. So another neat thing about tri-beam is we can get out information about the defects as well. So this is an example of a tri-beam data set where we're looking at the geometrically necessary dislocation densities or GNDs for a low power and a high power condition. And one thing that is pretty neat about this is you see for the high power condition, we tend to see a lot of GNDs present along the center line of the melt pool, which again isn't too surprising if you think about those processing conditions and the higher power conditions where we tend to see keyholing and a lot of keyhole collapse, producing again increased defect content. And so this is an area we're working a lot more in more recently as well. So moving forward, we've been doing work on refractory alloys. So we started doing work on some conventional refractory alloys, niobium ti and niobium C103, which is really a baseline refractory alloy. And this work is also in collaboration with Teresa's group at UCSB. But these are some example images of melt pool tracks that we did. And my student Megan has been doing quite a bit of work trying to optimize the processing conditions that we use and control defects during processing. And then she's really been doing a lot of this solidification mapping and CET mapping. So shown here are just some examples for the niobium ti as compared to the C103 and the different types of solidification morphologies we get. So here for the niobium 47 ti, if we zoom in on the edge of the melt pool, we tend to see a rapid transition to dendritic growth at the melt pool edge. And if we look at where that is relative to our map, that actually tends to make sense. Whereas if we look at C103, we tend to see planar growth at the edge of the melt pool as shown here. And that is consistent with sort of where we are in terms of the processing map as well. She's then going forward and again using other metrics like primary dendrite arm spacing. And this is an example of her comparing calculated PDAS values to actually measured PDAS values, which tends to match pretty well. And then again, trying to better understand the GV conditions we impart relative to columnar to equiax transition. And this is an example for a low power and a high power condition. And we can see for low power, which is actually our trace here in red, we would expect to remain in the columnar regime, where if we go to the high power in this case, we tend to cross over into CET at the top of the melt pool, which indeed we tend to see in this case. And so this is now making some assumptions about nucleation site density. This is kind of a fudge factor in these approaches. And this is sort of bound right now, at least for the moment, with some tri-beam data sets that were generated by Andrew Polonsky, one of Teresa Pollock's former graduate students. We've now moved on from classic refractory alloys to these refractory multi-principal element alloys or refractory high entropy alloys, which is a pretty interesting area to think about. So here, Megan is not only continuing to do these processing optimizations, but also looking at different alloy compositions and trying to predict alloys that could mitigate crack susceptibility. This is a nice example, alloy D here that oddly has some tungsten in it, actually suggests that it has good crack susceptibility. And then she's looking at, in this case, in the middle here, total undercooling, comparing C103 to niobium ti and these different alloys. And we can see alloy D has a lot of predicted undercooling that's present. And then if we kind of compare the mapping that she's done and the GV traces that are going to be experienced in a melt pool track that we've laid down, she would expect to see some refined grains in the melt track. And indeed, she does see refined grains in the melt track. So this is an area that we're moving forward. These kinds of assessments are obviously much more complicated for multi-component alloys, and this is something we're trying to better understand. And I'll say Teresa has some students working in this space as well. We do know when we take all these different high melting point elements and put them together and alloy them together, that we do expect things like microsegregation during solidification. This is early melt track work that my student Abby did, looking at Scheil simulations as compared to EDS measurements for some binary alloys as compared to C103, and then a quaternary refractory multi-principal element alloy. And again, we tend to see differences in the interdendritic regions as compared to the dendrite cores. Why do I think that this could be important for things like solidification and additive manufacturing? In related work, I'm not going to talk about today. We've done quite a bit on thermomechanical processing of these refractory multi-principal element alloys, and we've shown some neat trends with respect to the segregation patterns that we develop. And what's important about that is if we have microsegregation that we get from solidification, often it's hard to homogenize this out or get rid of it. And so here you're actually looking at a molybdenum map of a multi-principal element alloy. And we can see in the dendritic regions, we have higher molybdenum content. In this case, it turned out we had higher zirconium content in the interdendritic regions. Then in this case, we actually went ahead and did thermomechanical processing. So here we're doing hot deformation at 1000 C at a quasi-static strain rate. And what you see is we start kicking off dynamic recrystallization or DRX in those interdendritic regimes. So we basically have a strength differential that we set up between those two regimes in the microstructure, and that starts phenomena like DRX with deformation. And that could even be important for things like, say, we build something with additive manufacturing, and now we want to go ahead and heat treat it. So I think that there's a lot to think about still in this space about living with some of the microsegregation that we develop during solidification and what that means for any downstream processing that we might do. In this particular case, we were actually able to recrystallize this alloy. So on the refractory alloy space at the lab, we actually have an ongoing project right now that involves not only Los Alamos, but also Livermore and Sandia as well, looking at refractory additive manufacturing. Um, and this really has a feedstock angle to it. We know that having feedstocks of refractory alloys, especially novel alloys, is really challenging and quite expensive. And so the questions we have kind of surround what happens if we use pre-alloyed powders or wires as compared to doing the alloying in situ with DED kinds of processing. And so our work at Los Alamos is really focused more on electron beam additive manufacturing. And the neat thing about the capability that we have in Sigma is that we have a dual wire feed. And so we can have wires of different elements that we do in situ alloying with. So that's really our focus in the work, whereas Livermore and Sandia are focused more on the powder processing kinds of processes. And then we really want to understand, again, the processing strategies, the feedstocks, the microstructures, and the properties that come out the other end. One really neat, or some neat advantages of EBAM or electron beam additive are, again, feedstock flexibility, the high deposition rates that we can have to make larger parts as well. And then the very important one for refractory alloys is high vacuum, especially important for these environmentally sensitive refractory alloys and refractory multi-principal element alloys. So switching gears a little bit, I'll talk about titanium. Um, we have done some work on Ti-64, which is really a ubiquitous alloy for aerospace kinds of applications. And here we've done work changing the processing conditions, so going from spot melts to a raster, and then the Hoff pattern, which is something in the middle. And here we actually need to worry about solid state phase transformation as well. So we can see that slow cooling rates tend to promote more colony alpha beta microstructures, where faster rates, we tend to get more martensitic kinds of microstructures. And early on in this work, we did some neutron diffraction, sort of up the build height, that allowed us to compare and contrast the textures we got for these different kinds of processing pathways that we used. And we tended to find that as we go up the build height, we don't see big changes in texture, but we do see texture changes when we change from a raster to a spot melt scan strategy, just as an example. We then coupled this with large scale electron backscatter diffraction as well. And here I'm just showing the two bounding conditions, the random spot melt and the raster scan strategy. And we know that in Ti-64, we can use the orientation relationship to actually go from the product phase back up into the parent phase. And so that's what we're doing here is back calculating the parent phase orientation for the random and the raster conditions. And we can see for the random condition, we have kind of a much more refined microstructure, where for the raster, we have a much more columnar-like microstructure. And if we look at that in terms of GV, we see in the blue points here correspond to random. We have a broader sweep of GV that correlates with our more mixed microstructure that we see as compared to the raster, whereas more red, that tends to be more columnar. So this all makes sense. My student Alec did a lot of work looking at the textures developed in the as-built condition and these diffusional and diffusionless kinds of microstructures. And he showed that different texture components actually tell you a lot about what type of microstructure that you've generated. And why we think this is important is that it means that you can do a build, go and assess the texture, and have a really good idea all the way back up to the high temperature condition, what the microstructure was like during solidification. And so we feel like this is a nice pathway maybe to qualifying and certifying TIE 6.4 and really understanding the processing conditions that are imparted. In addition to TIE 6.4, we've explored some metastable beta alloys as well. So the nice thing is you can retain the beta phase at room temperature, and with deformation, you actually can promote deformation-induced phase transformation. This is like in advanced high-strength steels, for example, where you have austenite, and with deformation, you undergo transformation-induced plasticity or TRIP to martensite. So this is some work we did doing ultra-fast diffraction at the advanced photon source of these little tiny tensile bars, pulling them apart at 1,000 per second with Kolsky. And what's neat about this is we can actually monitor the phase transformation. So here in blue, we're monitoring the reduction of the beta phase and the increase of the martensite that forms with deformation while we're kind of ripping these samples apart. So this was in TIE 1023, I should say. So in this TIE 1023 alloy, we also did some laser track melt studies. So this is an example of one of these track melts. We have this massive heat affected zone underneath where we see a lot of martensite product present in this heat affected zone, which is actually pretty interesting. And so one of my students, Chris, did quite a bit of work trying to understand the propensity for this deformation-induced martensite and these metastable beta tie alloys. So this is an example of a track melt and then a subsurface kind of region where we had retained beta phase. And so he did a lot of modeling trying to understand those local conditions and why we do or don't get phase transformation. And then sort of coupled with that, he was also looking at things like grain size effects and also orientation effects in terms of the propensity for transformation as well in the beta alloys. More recently, we've done some work on the alloy TIE 5553. In this case, we heat treated the microstructures to have different extensive alpha phase. And here we're comparing powder bed diffusion, laser beam to rot. And then in this case, we're more interested in the dynamic materials properties that we get out the other end with and without heat treatment. So kind of in summary, what we actually see here is as we increase the alpha phase amount, we obviously have higher strengths. But here we're comparing head to head the powder bed fusion to the rot condition. And what's neat is we see that the powder bed fusion tends to outperform the rot in all the conditions that we explored. If we look at the post-deformed samples of the powder bed fusion and the rot, again, the beta condition as compared to the heat treatment condition, as we tend to increase the amount of alpha phase, we tend to see decreasing localized deformation. And this is a nice example up top here in the corner where we actually see an adiabatic shear band that terminates at a melt pool boundary. And this may be why we see these improved properties with additive. Also shown here is a nice example of dynamic recrystallization occurring inside of one of these adiabatic shear bands and microvoid formation and coalescence and ultimately crack formation. For these beta alloys, we're obviously always interested in other aspects of the microstructure too. In this case, things like twinning induced plasticity. So we do see evidence of twinning. And also there's always the question about omega phase in beta alloys, whether it's athermal or deformation induced. So the last tie example I have is sort of more of a solid state example. So TIE 6.4 tends to have these elongated columnar grains where it was shown by a recent Nature publication that TIE copper produces these refined grains, and that was thought to be due to the constitutional supercooling during solidification. What's neat about TIE copper is that you actually form a eutectoid product in the solid state as well. And this is much like perlite and steels. However, this eutectoid product in Thai copper is at the nanoscale. It's much, much finer, which is pretty interesting. So one of the things we kind of postulated is in addition to solidification, you might also get grain refinement in the solid state by thermal cycling during additive manufacturing. So one could imagine whether or not you produce equiaxed or columnar grains during solidification. If you then go through the solid state transformation, kind of as shown here, with a fast cooling rate, you make martensite. With a slow cooling rate, you make eutectoid, much again like perlite and steels. And then what happens as you thermally cycle relative to the eutectoid transformation temperature? And so we did some controlled dilatometric heat treatments where we were cycling relative to that temperature, and we showed that we were able to refine and reset the microstructure and create refined grains just from solid state thermal cycling. So what's neat about this is it gives you another pathway in addition to solidification to refine the microstructure. We did a little bit of work after that where we did some DED builds in collaboration with Sandia National Lab, where we compositionally graded up the build height. We then laid laser track melts in that and then looked at the microstructure. And we tend to see around the eutectoid composition that we actually have CET. So we believe that we have both of these things happening, and it's more prominent, I would say, at the eutectoid composition. But again, this is a unique kind of system, maybe suited especially for additive manufacturing. More recently, we've been getting into the properties of these nanoscale lamellar kinds of microstructures. So this is a CCT diagram developed by one of my students, Zane, where we've gone in and now done some Kolsky high rate compression of these ultrafine scale microstructures. And we tend to see the fine lamellar condition performs much, much better than, say, the coarse lamellar condition, just as an example. And then the last example I'm going to show work we've been doing more recently. We've done quite a bit on 4340 steel, so it's kind of fun to get back into steel. Feedstock to parts, looking at powder bed fusion and electron beam additive. So this is an example, again, considerations like virgin and reused powders, monolithic builds versus designed and engineered lattice structures. Doing the modeling, I would say with Flow 3D and also Truch's powder bed fusion, which is a code that we have at Lano, trying to understand those processing conditions. Adapting that kind of modeling to EBAM scenarios and wire-based scenarios is another thing that we're doing at the moment. And then I would say also taking that to feedstocks to parts, especially also for these designed and engineered lattice structures. So this is an example of mechanical properties and performance, both with and without heat treatment. And here we're comparing just, for example, round specimens versus flat specimens. And it's interesting that you do see a difference. High rate mechanical testing, looking at the microstructures we develop with processing and really understanding those processing conditions. We see some unique things in steels that result in maybe some more bainitic or martensitic kinds of microstructures that we're trying to deconvolute at the moment. And then understanding from the topology point of view what we actually design to build versus what we actually do build with computed tomography, and then forward modeling the properties and performance for these lattice kinds of structures. So I think with that, in conclusion, state-of-the-art in situ characterization really allows us to understand solidification dynamics, including with additive. We've shown quantitative phase field modeling can predict the banding and growth competition. The G's and V's are really important, and when we combine that with the characterization and the theory, it really allows us to move forward with predicting and controlling the way microstructures develop. Crystallographic information, including in 3D, can really give us some important insights, and this is a direction we're moving more into. A lot of opportunity exists for metastable phases, solid state transformations, et cetera, to really match that to the AM processing signatures that we have, and also to exploit heat treatments and solid state types of transformations. And then the unique microstructure and defect characteristics may produce interesting mechanical properties. And again, this is an area we're getting more into. So with that, I'll throw up this list of acknowledgements really quick, and I will stop there and invite any questions that anybody might have.